For this week, I want to start with a quick video about the logistic growth equation. This is a density-dependent growth equation for populations, and we use it to demonstrate a bunch of properties that we care about, things like stability analysis. So I just want to sort of lay out the basics of the logistic equation and logistic growth. So share the screen, and this will be pretty straightforward. I'm not going to get into the real details and nitty gritty of it. I want to keep it more at a sort of heuristic level. All right, so let's just think about population growth in continuous time, first of all. So suppose we have, what is that? No way. Sorry, I don't know if you could see that. Suppose we have a population that grows at a constant rate. So we have an equation, differential equation, change in n, population size with respect to time, is equal to an intrinsic rate of increase, a growth rate, which is basically the difference between births and deaths, times the population size at a given time. All right, so without getting into the details of its solution, it's pretty straightforward. You separate variables, you integrate. You can solve this so that your population size at time t is equal to the initial population size times e to the rt, e being the base of the natural logarithm, right? So this populations grow exponentially if they grow at a constant rate. That's actually what exponential growth means. It means it's growing at a constant rate in continuous time. So we can make a plot of this. We can do time t, we can do population size n, and what's it going to look like? It's going to start from n0, say right there, and it's going to grow without bound. Okay, and it's going to continue growing at a rate e to the r, right? So that's probably not super realistic, right? This is growth without bounds. Suppose we, there are resource constraints, right? You can't feed an infinite number of organisms, right? So presumably at some point, population growth will slow down as maybe the deaths start to increase relative to the births, and maybe they even, the growth rate will go negative at some point because you'll have exceeded some sort of capacity for the environment to maintain your population, which we call the carrying capacity. So let's think about a model that incorporates some sort of feedback, right? So that the growth rate at any given point in time is a function of the population size. And we're going to focus on the simplest model. It's a linear model, and it only depends on the total population size. Okay, so we can write this sort of generically, dn dt equals n times f of n, right? So f of n being a function of the population size. And I mentioned that we're going to use a linear model, so for f of n, and that model will simply be r times 1 minus n over k. All right, so we call k the carrying capacity. And let's just think about a couple limiting cases to fix our ideas. Suppose that, suppose for example, that n is equal to 0. What happens? Well, if n is equal to 0, then this fraction here, n over k, is equal to 0. So we just have f of n equals r times 1, which is just r. We're back to our original unbounded equation, right? So at the outset, at the early stages of population growth, this model, it's called the logistic model, right? Behaves just like the exponential growth model. There's an early exponential growth, all right? So this implies that f of n That's what I'm looking for, is equal to R. All right, so let's look at another limiting case. Let's look at K as N equals K. What happens? Well, now we have K over K, right? So that's 1. So 1 minus 1 is 0. And so 0 times R is 0. So when N is equal to K, f of N equals 0. All right. So that gives us a little sense of the limiting behavior here. Um, I'm not going to show you how to solve this. You integrate it again. You use the method of partial integration by partial fractions. It's a little more involved, but it's pretty straightforward. Um, what we will get is something that looks like it's a sigmoid curve, okay? And it will, this right here would be equal to K, right? It asymptotes to K and it stays there stably if it's not perturbed, okay? Um, this is the curve you typically see, this S-shaped or logistic curve. That's why it's called a logistic growth model. There's actually a more useful way of plotting these data, and that's to actually plot this thing on the right-hand side of the equation directly against n. Okay, we call that the recruitment curve. And the recruitment curve is generally a more interesting thing. And we'll actually call that delta n. We're going to plot that against n, right? Because that's the amount the population changes in a small time step. And for the logistic model, this recruitment curve looks like, no, that's not good. Try it again. It's perfectly symmetrical, right? And it's just kind of hard to draw a perfectly symmetrical curve. All right, and this is K, all right, and this is 0. When the population size is 0, the population doesn't grow. When the population is size K, it doesn't grow. All right, and the population grows at a max when n is equal to K over 1/2. This is just a feature of the logistic model. There are other types of recruitment curves for different types of models that will be asymmetric and they'll give you different maximum recruitment. This is sometimes called the maximum sustainable yield in wildlife management, that sort of thing. If you wanted to keep, for example, a population of deer, if you wanted to manage that population, keep it down, you could hunt out K over 2 if you knew what the carrying capacity was, right? It's a big if. You could hunt K over 2 and you get the maximum yield without causing the population to decline. So that's an important applied parameter. Just as a last thing, let's think about this recruitment curve, right? So this is the change in population size as a function of the size. So let's look at when you're at 0, what is the change if you go up a little bit? If you're exactly 0, you can't grow because there's no one to reproduce, right? But if you're just a little bit above 0, what happens if you get pushed just slightly above 0? Well, you're going to increase in population size. That's what this curve that's above 0 tells us. So we can get an intuitive sense here that if this is an equilibrium, right, where an equilibrium is where this model doesn't grow, the 0 equilibrium is unstable because that arrow is going to point away from it. Now, it doesn't make sense to talk about negative population, so there's no arrow in the other direction. Okay, what happens if we're somewhere around here, right? Well, the growth is reducing. It's going like it's decelerating, but it's still growing, right? Any part of this curve that's above 0 means that the population is still growing. It's just growing at a slower and slower rate as you approach K. So that means that you're still pushing towards K, all right? And what happens if you're above K? Well, it actually makes sense. So you can't have negative numbers of animals, right, or of plants or whatever the population is, but you can have negative growth, right? So this curve actually does, theoretically keep going down here. And what that means is that if we find ourselves somewhere over here, for some reason the population overshoots, what's going to happen? You're going to have negative growth, right? You're going to have contraction of the population, which means that it's going to come back to your equilibrium. So we will say that the carrying capacity in this simple model without any perturbations or anything has two equilibria, and one of them is unstable because the population tends to move away from it, and one of them is stable because the population tends to move back to it when it's perturbed. And we're going to look at that more formally because using a thing called linear stability analysis, which is an incredibly powerful tool. And the thing that's so great about linear stability analysis, more even than like your ability to actually calculate the rate of return to something, is the intuition it gives you about broader classes of models. And that's what I'm hoping to try to foster here a little bit. So that's the introduction to the logistic model. The next video will involve actually calculating the linear stability analysis of the logistic model.